I decided to add this little piece of marine ecosystem feedbacks. As I mentioned, the authors are predominantly terrestrial ecosystem people, land atmosphere process people. So there is actually a clear indication of biophysical feedbacks in addition to the biogeochemical feedbacks from the ocean ecosystem as well. El Nino serves as, again, the best example of how this feedback actually works, and there are many modeling studies from this, including my own work. So let's look at El Nino in this context as well in a little bit more detail than we have done this far. We talked about the zonal mean meridional circulation, Hadley cell, Ferrel cell, polar cells, and so on. But if we open up like an accordion, we briefly mentioned the zonal circulation as well. So what was happening? You have maximum heating on the equator, so you have rising air, evaporation, condensation, and rain. But in the zonal mean meridional section, it looks like it's raining in the middle, and then it's dry in the subtropics, and then storm tracks and so on. But when you look at the zonal contrasts, there are few spots where the rainfall is very heavy. So there is the Western Pacific Maritime Continent, there is the Amazon, and there is the other side of the Atlantic as well. And you can see that just like Hadley cell in the meridional direction, there is the Walker cell associated with Sir Gilbert Walker, who was the first one to figure this out. So this is the zonal cell. So the convergence into the rising air is not only from the polar regions, but it's also from the east and west. So you can see the convergence feeding the rising air and the heavy convection with almost 5 meters of rain per year over here. That air again hits the ceiling just like the Hadley cell does. It goes east to west. There is of course the Hadley cell component. We are just focusing on the zonal circulation here, and it sinks in the eastern Pacific Ocean and the Western Indian Ocean. So you have the African monsoon here and the Amazonian convection over here. Did I say South America here before? Anyway, so this is the Pacific Walker cell. So you have the trade winds which are converging into the ITCZ as we saw, and the ocean water is being pushed to the west as well as being diverged. So if you look at the east-west contrast, then you have upwelling around the Galapagos because winds are pushing water away from the equator because of Coriolis. Colder, nutrient-rich water is coming up, and during an El Nino, for whatever reason, we don't always know exactly what triggers it, or whether this is just an oscillation that would go on anyways. Trade winds weaken, or you have anomalies of winds from here pushing the warm water eastward. So warm water, convection, cold water, sinking air, high pressure. So you have a pressure gradient, you have a temperature gradient, and because you are near the equator, Coriolis is weak or zero on the equator, so the pressure gradient and temperature gradients can actually drive winds. And because Coriolis is weak, you can just have directly proportional winds to pressure gradients, right? During an El Nino, then the whole system relaxes, so you have anomalous subsidence over the region where there is usually ascent and heavy rain. So the convection and the ascent move to the central eastern Pacific and create warm anomalies because the trade winds are weaker, upwelling is weaker, cooling is reduced, and then you also change the temperature gradient, so there is a positive feedback, and there is also subsurface ocean changes happening in the thermocline and so on. I'm using these terms like thermocline. If you are not familiar with those, you can go and look my podcasts on those on YouTube as well. Okay, so that is the El Nino response of surface temperature, which as we saw has teleconnections all over. And reduced upwelling in the case of nutrient supply means reduced primary production. So there is an anomaly in primary production as well, as we will see. What does that have to do with feedbacks? We will see that during La Nina, for example, there are colder than normal temperatures. Here now subsidence is stronger, ascent is stronger, Walker-Cell is stronger, so upwelling is stronger and primary production is stronger. So there is a clear signature in ocean chlorophyll. This is the ocean chlorophyll during El Nino, normal years, and La Nina years. So you can see that the compared to normal or La Nina years, the phytoplankton or the primary production is greatly reduced, associated with the very warm temperature of El Nino. No significant anomalies here because it's a ENSO neutral year, and this has got cold anomalies because it's a La Nina, and primary production is enhanced as well as extended further west. Okay, what does this do? Essentially, if you look at the penetration of sunlight into the ocean, UV is trapped in the top, and then the longer wavelengths are absorbed in the very short distances. The green and blue penetrate much deeper, so the primary production is going to affect the penetration of radiation and energy into the ocean, which means it's going to affect the vertical structure, the thermocline, the SST cooling, sea surface temperature cooling, and so on. Okay, so whether it's a seasonal change in upwelling or whether it's the El Nino La Nina timescale change in upwelling, you are going to get a change in the energy balance in the ocean. So El Nino has a warming, reduced upwelling, reduced primary production, which means the impact of marine ecosystem on the heat budget of the upper layer is reduced during this time, whereas during a La Nina, stronger upwelling, more primary production means more energy is trapped near the surface because of the shading effect of the phytoplankton. So the surface is actually not getting as cool as it should if this trapping of the radiation was not happening. So the key question then is the La Nina limited in its amplitude? For example, if you look at the warm anomalies during a strong El Nino of 3 degrees or greater, and if you take the strongest La Nina in the history, you will not get such strong sea surface temperature anomalies. So there is an asymmetry in La Nina. There are other asymmetries, like El Nino is a discharge of warm water, so it's only happens 1 year, 6 to 18 months, and very unusual to have back-to-back El Ninos. There is just not enough fuel for it. Whereas La Nina can continue for many years because trade winds can get stronger, upwelling can keep on going, and ocean can keep on soaking up heat, and there is no limitation on it. There are other details, but essentially primary production could be limiting the amount of warming you would get during a La Nina. So that's kind of the biophysical feedback from the marine ecosystem to a fundamental mode like the El Nino and La Nina. Okay. Obviously, associated with that, there are changes in CO2 fluxes. For example, stronger upwelling brings up more carbon-rich water to the surface, increases the surface atmosphere partial pressure difference of CO2, and drives outgassing from the ocean. So strong La Nina has more CO2 going out, whereas during El Nino, the CO2 is reduced. In the ocean, there is a biological pump which is related to photosynthesis and carbon uptake, and a solubility pump where cold waters with high CO2 control the fluxes across the air-sea interface. Okay, I just wanted to give you an exposure to that potential feedback in the marine ecosystem as well. We've looked throughout the chapter at feedbacks between vegetation, biophysics, and biogeochemistry, but in the ocean also you have the same biophysical and biogeochemical feedbacks associated with marine ecosystems. And there is lots of work arguing that this feedback is also strong enough to affect cyclones and hurricanes because they take the energy from the ocean as well. And when they churn up the ocean and suck up the water, there is always increased primary production behind behind a cyclone, a hurricane, or a typhoon. So how does that affect the next cyclone, for example, in terms of the heat content in the ocean? There are also feedbacks happening at subseasonal timescales with Madden-Julian oscillation along the same lines, and so on. So that's just a brief run through feedbacks between marine ecosystem and climate, both in biophysics and biochemistry.